So, let us just recall from the last lecture, I was talking about the shortest path problem, and we discussed Dijkstra's algorithm, and Dijkstra's algorithm required theCij's to be non-negative. Then we also discussed Floyd and Warshall's algorithm, which could take care ofCij's being non-negative, being negative also. And actually, the Floyd-Warshall algorithm gave you shortest distances between a pair of nodes, every pair of nodes. So, and I had showed you that if for the Floyd-Warshall algorithm, yeah, this is when this is the shortest path problem, right? And we could be said that Cij's could be negative also. Okay, could be negative. So in that case, I showed you that if UIIM became less than 0 for some I and some M, then this implied that negative cycles were present in the network, right? And therefore, shortest paths lose their meaning, because I can keep going around the negative cycle and reduce the distance between any pair of nodes, right. So, therefore, the moment you discover that there is a negative cycle present in the network, you stop computing the shortest path distances. Okay. And this simply said that for some node, that means the diagonal entry, because I to I, the path from I to I, including nodes up to from 1 to m minus 1, that became less than 0, then you said that there is a negative cycle present. So, this will happen for some I and some n up to n plus 1, because that is the number of iterations for n for the Floyd-Warshall algorithm. Okay. So, now suppose you so then there is a another problem related to shortest path problem, and that is the longest path problem. Okay. You also want to, and we will discuss the problem sometime later, in which we really have to compute longest paths between between pairs of nodes. Okay, so longest paths. But again, here also you see that if the longest path problem, if the network has a positive cycle present in it, then the same argument applies, that I can go on increasing the longest path distance by traversing the positive cycle as many number of times as I wish to, right. So, the longest path problem also is feasible if we can ensure that there are no positive cycles present, right. So, now to look at it, so that means if yeah, so what we will do is replace each Cij by minus Cij. Okay. So, if you replace each Cij by minus Cij, then and solve the shortest path problem, then, right. That means first replace all the Cij's by minus Cij, and then you look for the shortest path between the specified pair, and the shortest path computation will give you the longest path, right. So, again, so same thing here, that in case while solving the shortest path problem, we discover there is a negative cycle, it would imply that with respect to the Cij's, that corresponding cycle has positive length. And so, we will again say that the problem is not feasible, right. So, therefore, here depending on whether your if your all Cij's are non-negative, then the minus Cij's will be all negative. So, you will have to apply Floyd and Warshall algorithm for the corresponding shortest path problem, and then whatever results you have for the shortest path problem will apply here, and then you can translate them to the longest path problem. Okay. So, that is another thing. Then the other aspect that we want to look at now is, since we have discussed the min-cost-flow problem, we have discussed the shortest path problems. So, I want to now look at the sensitivity analysis or the post optimality analysis for these problems. So, for the shortest path problem, the only thing to change is the Cij between for a particular arc, right. So, here for example, now the thing is that the moment you lose the linear simplex, the simplex algorithm structure, you the post optimality analysis becomes you have to do more effort, and it's not as smoothly done as you do it for the simplex algorithm. So, here for example, yeah, let me yeah, so here let's say look at so we had at some time ago discussed this problem with you, the shortest path problem, and this was your tree of shortest paths, right. Tree of shortest paths, we had computed this from node 1, right. So, this gives you, like for example 1 to t, the shortest path distance is 3, from 1 to 3 the shortest path length is 4, and so on, right. See, sensitivity analysis for the shortest path problem, and I was trying to show you the idea here is that if you change the Cij when arc ij is not present in a shortest path. Suppose we want to look at the what kind of changes we can make in the cost Cij for an arc ij which is not present in the shortest path. So, now before I do this, I will have you recall that see in the 29th lecture I had shown you that you see these Wi values which denote the shortest path length from node 1. So, then the corresponding dual variables, because the shortest path problem we could formulate as a linear programming problem, and therefore, the dual variables have a meaning here, and I had shown you that the pi i's would be minus of these Wi's. That means, pi i's will be the negative of the shortest path length from node 1, but whichever node you fix, and then you define your linear programming problem, and then you get the dual variables, right. Okay. So, if this is this, then and in fact, I would like you to using these pi i's, then you show that these numbers satisfy the, that means this problem is actually an optimal solution to the shortest path problem, by showing that for all arcs for non basic arcs, that means arcs which do not figure in the shortest path, the optimality criteria is satisfied, because for the arcs in the paths shortest paths, the dual constraints will be satisfied as equality, right. So, the first case we will consider is that of an arc which is not present in any shortest path. Okay. So, let us say 1 3 is one of those arcs which is not present on any of the shortest paths, and let me consider the length going up by the amount delta, right. So, the current the new length of the arc becomes 5 plus delta, okay. And the optimality conditions require. So, remember I had earlier lecture shown you that whatever the lengths of the shortest paths which are denoted by these circled numbers at each node, then the dual variables are negative of the length of the shortest paths, right. So, minus pi I is Wi, that means pi I is minus Wi. So, if you apply the shortest path condition, then this is pi 1 minus pi 3 should be less than or equal to C 1 3 plus delta. This is the new Cij or C 1 3. But so, substituting pi 1 is 0 because W 1 is 0, pi 3 is minus 4. So, plus it becomes plus 4 here, right, minus pi 3 is W 4, and so this should be less than or equal to 5 plus delta, which implies that delta should be greater than or equal to minus 1. So, that means the current solution will remain optimal. This will remain the tree of shortest paths for all values of delta greater than or equal to minus 1, which is expected, because as it is 1 3 did not figure in any of the shortest paths, and if the length goes down even by 1 unit, even then it does not become a candidate for being on one of the shortest paths. But in case delta becomes less than minus 1, then you can see for yourself that arc 1 3 will get replaced by 2 3. Of course, this is a small example, but essentially what will happen is that you will be you will have to start the labeling procedure again, because remember we do not have the linear programming structure anymore. We were, because we to exploit the structure we have used Dijkstra's algorithm. Of course, this is the case when I am taking all Cij's to be non-negative. So, in that case you will have to start your labeling again, but you can see right away from here that if 1 2 so 1 3 becomes, let us say for example, delta is minus 2, then this will become, this length will be 3 and the shortest path will be 1 3 instead of 2 3. Right. So, 1 3 will come into become a shortest path and this arc 2 3 will go away and so on. So, but essentially the moment one of the lengths changes, you will have to start your labeling procedure from where that arc can come into the basis or can figure in the shortest path. Now, similarly, let us now go to an arc I j, which is on the shortest path from 1 to n. Let me consider that case and then similarly you can then see how to handle the case when I j is in one of the shortest paths, but not on the path from 1 to n. Different cases, but the treatment is the same. Okay. So, now what happens is that when C 25, for example, take the arc 25 which is figuring on the main shortest path from 1 to 6. So, 25 goes up from 1 to 1 plus delta. In that case you see the shortest paths will change, because if this becomes 1 plus delta, this length becomes 4 plus delta and this will become 7 plus delta. These paths path lengths will not be disturbed, right. 1 to 2, 2 to 4, 3 and 3 to 4. So, it is only this becomes 4 plus delta and this becomes 7 plus delta. So, now we will have to check for optimality conditions, because we want to make sure that for what values of delta the current solution will remain optimal. And so, I have computed it, for example, for arc 2 4, C bar 2 4 will be 5 plus 3 minus, okay, this does not change, because your 2 and 4 have not changed. So, okay, that remains optimal. So, anyway, this is 8 minus 6 which is 2, which is greater than 0. So, no lower bound for delta. Why am I saying that here? Yeah, okay. No, not in this case. Okay. But okay, this comes later, fine. Yeah. So, this is C bar 2 4 anyway remains non-negative, and then C bar 3 5, if you look at the arc 3 5, then the optimality condition requires 4 plus 4 minus delta, right, because C this thing is the cost is 4, then minus pi 3 plus pi 3 minus pi 5. So, this becomes this. So, that gives you delta less than or equal to 4. Similarly, if you compute C bar 4 6, the number comes out to be, this gives you delta less than or equal to 3. Since both of them have to be satisfied, your delta has to be less than or equal to 3. Yeah. Now, from here I am saying that since 2 5 figures on your shortest path, therefore, it will not hurt if the cost of, if the C 25 goes down and there is no limit. So, there is no lower bound, but again the algorithm that we have used here, the requirement is that all C I J's must be non-negative. So, the validity of the algorithm will be questioned in case I allow the C 25 to become less than 0. So, therefore, I am saying that logically it does not require delta to be a lower bound, but we will, since we are using the algorithm which requires C I J's to be non-negative, we are going to say that delta should lie between minus 1 comma 3. So, in this interval, as long as delta varies in this interval, your current solution will remain optimal. That means, your path length will be 7 plus delta. So, anywhere from so that means, right now this can go up to 10 or this can be 6. So, the shortest path length, this path will continue to be the shortest path and the path length will vary from 6 to 10 as delta varies, and after that if delta goes beyond 3, then this path will not any longer be the optimal path and you will have shortest length path, I mean path lengths which is less than 10, right. So, this what will happen. And similarly, then you can even question, you can ask a question if arc 4, suppose the current network does not have arc 1 4, right. And so, you may want to ask a question, suppose it is considered that the a new route may be added, and therefore, you would want to know when is it profitable to add the route 1 comma 4, right. And so, therefore, you will want to find out, see currently the shortest path length from 1 to 4 in your shortest path tree is 6, right, because these are the shortest path lengths from node 1. So, the currently it is 6. So, immediately you see that if you want to add this arc, if you want to construct this, then the cost, the length of this route should not be, that means your C 1 4 should be less than 6 or less than or equal to 6. In that case, you will have an alternate optimal solution. but otherwise you will have to again if you want to add this root, then you will have to start your labeling procedure again and then find out what are. So, you will use C14 as a unknown number, and then the labeling procedure will tell you as to or okay. Yes, so you can do this way, but immediately by looking at the shortest path tree, you can find out what should be the cost of the length of the route 14, so that it becomes profitable. Let us say C14 is equal to 5, then it will be worth considering to include the arc 14 in your to construct the arc, because your shortest path length up to 4 will go down. Okay. Of course, it does not figure, this arc 14 will not figure in the shortest path from 1 to 6, but you see again here I am trying to what I am trying to point out is that suppose C14 arc is added and the cost is 5, then you would have added this arc and the path up to here is the path length is 5, right. Now, from here you want to reach 6, then this cost is 4, right. So, then 5 4 9, 9 is not less than 7. So, therefore, adding this route will not cut down on your shortest path, but you can compute, you can make this computation and find out if you at what cost it will be profitable to add 14, in the sense that your shortest path length reduces. Say for example, you can immediately make the computation here if this is C14. So, here for example, direct route. So, this will be C14, right. So, then if you add, this is 3 plus 3 6. So, one route would be plus 6 and this route is plus 4, right. And then, so C14 plus 4 is the smaller one, this you want to be less than 7. Then this will tell you that the C14 should be around 3 or less than 3. Then it will be profitable to add. So, you can whatever question you want to ask, now you know how to answer that question. So, this is the whole idea, this kind of sensitivity analysis you can do, right. Then another interesting aspect of sensitivity analysis is that suppose now let me define Wij psi as the length of the shortest path from 1 to n. So, remember I am only talking of the shortest path from 1 to n, I am not talking of other shortest paths, because this has more meaning. Otherwise, you can do the same analysis for any shortest path. So, when Cij is psi, okay. So, suppose the current length is psi, and so I am defining Wij psi as the length of the shortest path, right, and of course, all other arcs remain the same. Now, if Ij is contained on a shortest path from 1 to n, when Cij is 0, then the shortest path will remain shortest as psi increases and goes from 0 to this number. And remember, when we say that the length of an arc has become infinity, it implies that the arc is not there, because obviously you are talking in terms, you have finite length. So, shortest path length will be finite. So, any arc capacity going to infinity means that it is not part of the shortest path, either it is destroyed or it is not in the not. So, therefore, as long as the current path remains the shortest path from 1 to n, that means that Ij is the arc Ij is figuring on that shortest path. So, then and as the capacity of the arc Ij keeps going up, the length of the shortest path, just as here I showed you that from 1 to 6 the path length will go from 6 to 10, as delta varies from -1 to 3, right. So, but after this this current path will not remain optimal, and that means arc 2 5 will go out of the shortest path and a new shortest path will come in. So, therefore, this path length the psi can increase up to this number, and then the moment psi becomes bigger than this number, the shortest path from 1 to n changes. So, it does not contain arc Ij. So, this is the idea, and we will define a Cij star as the critical capacity, critical length of arc Ij, okay, which is W infinity minus Wij 0. So, destroying the arc is equivalent to making its length equal to infinity. This is the whole idea, and then so you want to ask a question, shortest path length will go up by maximum of this, right. See, if Cij is less than Cij star, then the arc Ij is present in the shortest path, right, and then so the max here will be this number, because 0 is less than this number, this difference is positive. So, as long as Cij star is greater than Cij, your arc Ij can remain on the shortest path, and that will be the length. So, the arc I j will remain on the shortest path, right, and the moment C I j becomes equal to C I j star, which I said here also, the moment it becomes this, or C I j is bigger than C I j star, then this will become, because this number will be negative, and so max will be 0. So, essentially your shortest path length will go up by this amount if C I j is less than C I j star. So, then you again here you want to find out, the question that you can ask here is, which is the arc which gives you the minimum increase in the shortest path when destroyed, or the other question, when will it give you the maximum increase in the length of the shortest path when it is destroyed. So, in times of strategy, war and so on, other situations, you want to consider arcs. For example, if an arc is likely, if a route is getting very bad, needs repairs, then and you have limited resources and then one route which needs repairs, then you would want to know which is the route which has to be repaired first. That means, if it gets destroyed, if it is not used, then the length of the shortest path will go up by maximum amount. So, these are the kind of questions you would need to ask. Say for example, if you look at the basic non-basic arc 1 3, then you do not expect that. Okay, so let us just simply, I will just do it for one this thing. So, here critical length. Critical length. So, you want to compute C 1 3 star. I will just give you one example and then you can compute the thing. So, C 1 3 star is equal to what? So, what is your W 0? So, when this is 0, you see this is right now is not figuring in the path. Okay, 1 3 it will not matter, because yes. So, C star 1 3, if you have C critical length for C 1 3 star, you see W infinity of course is 1 3 infinity is 7, because R 1 3 is not figuring in the shortest path and the current length is 7 from 1 to 6. But when its capacity is 0, you see I have quickly computed the thing, and you can verify if this arc length is 0, then you see your shortest path would be 2 and 4. Right. The shortest path will be 1, 3, 4 and 6, and the length of this path would be 6. So, that is W 0, right, and so the difference is 1 unit, but then max of this is 0 comma 1 minus 5, because the current capacity is 5, length is 5. So, 1 minus 5, which is minus 4, therefore, this max, this is 0. So, essentially what we are saying is that for arcs which do not figure in shortest path, their change in the by the critical capacity would be something which is smaller than the current capacity of the. So, in fact, what I am saying is that this number would be negative, right, and so there will be no change in the length of the shortest path. But for an arc 2 5 which is figuring in your shortest path, you see this you can compute that when it is 0, when it is infinity, when 2 5 is not figuring in the, that means its capacity, its length is very large, then the path will be I think 1 3 5 6. 9 and 3, oh, okay, maybe 11 or 12, I do not know. So, figure out 5 to 7, it will be 1 3 4 6, 5 and 2, 7, 7 and 4, 11, right. So, this is 11, because 2 5 is not figuring, and then W 0 is 6, right, because this number is 1. So, it becomes 0. So, therefore, the capacity of the path will be 6, and so this number, therefore, this is equal to 5, right, and so max is 4, and therefore, here when you the difference in the this thing shortest path length will the path length will go up by 4 if the arc is destroyed, right. So, therefore, the question that one wants to ask here is, so by through this analysis you want to ask the question, find an arc which when destroyed increases the shortest path length by smallest amount, right. And so, these are the kind of questions, or the opposite question also can be asked, destroying an arc, there is maximum increase in the shortest path and so on. So, these kind of questions can be asked, and so and what I wanted to point out here is that because we have not solved the problem, we have not, by the labeling algorithm we have obtained these numbers. So, therefore, what will happen is that when a label changes for a node, then you have to start your labeling algorithm from that point onwards, because then the other labels will change, right. The computations before that, before this node got labeled, they remain intact, but the other computations have to be made, and this was what you will have to do for the Floyd-Warshall algorithm also, because Floyd-Warshall algorithm anyway cannot be formulated as a linear programming problem, because it is a multi-objective problem. You are finding shortest path between pairs of nodes. So, there also if a particular Cij changes, then you see, for example, if this changes, then you see there you are computing the numbers Uij(m), right. So, then m is 4. So, here you are computing these paths when you are adding using nodes up to 3, 1, 2, 3 only. So, those will remain intact. If this length has changed, then obviously the Uij 4 and 5 and onwards will change. So, you will have to recompute from that point onwards. If this is the kind of thing you will have to keep track, and so you see the moment you lose the simplex algorithm framework, then sensitivity analysis becomes you have to do more work for it. So, now we will consider the sensitivity analysis of the supply and demand. That is, if the numbers here increase and decrease, then can we adjust the current optimal solution and take care of the changed demands and supply. So, here since we are working with the condition that your new supplies and demand should also again add up to 0. So, if I increase the, suppose I am taking so delta to be positive. So, if I increase the ith supply by delta amount, then some demand must also go up. So, that means the Bj will be negative. So, minus delta will get added to it. So, the supply and demand will remain the same. So, let us just take some pair Ij. So, supply has gone up by delta and the demand has also gone up by delta units. Now, since in the current solution the tree that you have of the basic arcs, there will be a unique path from I to j in the current tree. I should have said the current basis tree. Okay. And some arcs will be forward arcs, that means arcs which have the same orientation as from I to j, and the other arcs which I will denote by p lower bar. So, p upper bar is the set of forward arcs in p and p lower bar is the set of backward arcs in p. And then to maintain feasibility, the maximum amount delta k by which flow on arc L k can increase. You see, now along this path you will try to, because the supply has gone up by delta units and the demand also. So, you want to see whether on this path p you can have increased flow. Now, what does that mean? It will require that, see, for any arc in the path, for any L k in the path, if it is a forward arc, then its current flow must be less than the capacity, because then only I can increase the flow. If the arc is saturated, then there is no point, I cannot increase any more flow on arc L k. Similarly, if it is a backward arc, it is in lower bar, it is not very clear, let me make it, this is p lower bar. So, if it is a backward arc, then it must have a positive flow, because then I will increase the flow in the opposite direction, right, which means that the flow on the arc L k will decrease. So, if all arcs in p satisfy this condition, then I will say that it is possible to increase the flow from I to j, and by how much amount? So, delta will be the minimum, because so that means the augmenting capacity of each arc on the path p I will compute by this, and then I will take the minimum, because the minimum number minimum of all the delta k's is the amount by which I can augment the flow or increase the flow on p, right. Now, if delta, so therefore, delta lambda is the amount, is the augmenting capacity you can say of the path p. Now, if delta is less than or equal to lambda, fine, because we want to increase the flow by delta and the capacity of the path allows you to do it. So, then I can increase the flow, and since the optimality criteria continues to be satisfied, I have not disturbed my basic feasible solution. Therefore, the current solution is optimal. Of course, the cost will go up, because you are having increased flow on the network, right. Now, the problem comes when your delta is greater than lambda. So, then of course, you will just augment the flow on p by lambda, and now you have to worry about the rest of the remaining flow delta minus lambda. So, the question is to see if flow can be augmented by delta minus lambda units, and here we will now need to, because the current solution you will say is not feasible.
and so you have a situation for a dual simplex pivot, because your optimality criteria is currently satisfied, the basis is satisfying it, but the basis is not a feasible solution. So, now we start looking at how to implement the dual simplex pivot here, and again because of the simplified structure, you see that the step the pivot dual simplex pivot also gets simplified. Now, first of all, because the capacity on arc P did not you to have flow more than lambda units. So, there will be a blocking arc, in the sense that blocking arc, as I said, it will either be saturated, right. That means, after augmenting the flow by lambda units on P, a forward arc. So, for P q the flow plus lambda became U P q, and so it got saturated. Therefore, I cannot increase the flow anymore on arc P q, and if it was a backward arc, then the flow that you reduced on the arc was equal to the current flow, the flow on the arc, and therefore, it became 0 now. So, therefore, I cannot use P q as a backward arc also. So, therefore, P q is a blocking arc, right. Now, so we will drop arc P q, and we will try to see if we can change the basis or the basic tree and get another route from I to j. So, that I can have increased flow on that route or on that path, right. Now, once you drop an arc P q, remember on a spanning tree, if you drop the arc P q, then the tree gets divided into 2 subtrees, let me call them T 1, T 2, right. It becomes disconnected, because spanning tree is a minimal connected tree. So, the moment you drop any arc from that tree, spanning tree, it becomes disconnected. So, you have 2 portions, disconnected portions T 1, T 2. S 1 are the nodes of T 1 and S 2 are the nodes of T 2, right. And suppose I belongs to S 1 and J belongs to S 2. Then see, what is happening is that S 1, S 2, the node sets, this is a cut, in the sense that, and I am just later on, of course, we will have more occasion to use cuts heavily, but now here what I am saying is that a cut set means that it is a partition of the node set. So, node set V. So, S 1 union S 2 equals the node set V, and they are disjoint, right. So, this is how you define a cut, and the cut set will be all arcs which are either from S 1 to S 2, that means L comma k, such that L is in S 1 and k is in S 2, or its arcs going from S 2 to S 1, that means L is in S 2 and k is in S 1. So, this is all the possible cut sets. That means, you have partitioned the node set, your I is here, your j is here, I am saying this is S 1, this is S 2, then you have arcs are going from this to this, or you have arcs going this way. Okay. So, this is all, and therefore, you can see that any path from I to j will have to use one of these arcs, either going from here to here or from here to here. So, this is what we are saying, any path from I to j will contain an arc from the cut set S 1 comma S 2, and this is where we will try to now locate the arc on, so that I can have a path from I to j. Okay, a few things are not being explained in detail, but later on when we do the max flow also, you will hopefully get a better feeling for this. So, now anyway, the idea is to look for a valid arc. A valid arc from among these should have positive capacity left on it, and backward arc must have positive flow. So, these are the apart from P q, P q became a blocking arc. So, I need arcs from here to here which have positive capacity, or from here to here. Okay. So, it is a positive capacity forward arc, or it is a backward arc with positive flow on it, right. So, among all valid arcs, choose that one which has minimum of C bar L k. Okay. That means a relative cost, and this is your dual pivot, dual simplex pivot. Now, please just stop here for a while and see why I am saying this, because remember, for the network problems we had shown that your Yij's are either +1, -1 or zeros, and the ones the dual simplex pivot, that the element that you choose must have a corresponding Yij negative, right. And so, we do not need the ratio, I mean the minimum ratio will actually be the minimum of the CLK bar absolute value. So, this is the arc which will be, and so once you choose a valid arc to be satisfying this condition, then you see your optimality condition will continue to be satisfied, right. And so, then what we will do, if we have a valid arc, then among all the valid arcs we will choose the one which has the minimum relative cost in absolute term, and then we will try to flow as much arc as possible on the path from I to j. right. So, what you can say is that if I have an arc like this, then see the flow from I to up to this point is there, then since this has positive capacity, I will increase the flow on this. So, the total and then come up to j point, right. So, you can then increase the flow on this path, finding out the capacity of the path the way I have told you earlier, right. And again if there is still some left over, you will do the same thing, you will again find a blocking arc and try to find which is the arc which if there is any more valid arc or not. So, if you ultimately cannot find any valid arcs and you still have some leftover flow, then that means this is infeasible. That means I cannot allow for increase of delta units here, since I am not able to accommodate delta units in the network and increase the flow, right. But if your dual simplex pivots allow you to keep increasing the flow, you will go on doing it as long as you can and then stop, right, if you do not have any invalid arc, right. So, this will this is the process we will use to find out, and now I will take up an example to explain the various steps that I have told you. So, let me now show you for the min cost flow problem. This is what we are considering now, the sensitivity analysis for the min cost flow problem, where the supply and the demands have been changed. So, let me this is the network flow problem, right. The first number here is the cost and the second number is the upper bound the flow in that particular arc. So, and of course, I have not shown the demands and right, okay. The demands and the supplies could also be shown. This is 5 and this is 3, that means 8 units are available here, and this is -2, -3 and -3. So, the sigma BI's add up to 0, right, I varying from 1 to 5. So, this is what you have, okay. And this is now optimal solution. You can see that of course, this is the later step, but 5 units are leaving node 1 the supply point, and since these 2 are demanded. So, 2 are reaching here, then here for example, 3 units are coming here and then 3 plus 6 units must go out, right. So, from here 4 units are going 3 units are going to 4 and 3 units are going to 5, which are the respective demands of the 2 nodes, right. So, this is an, and you can check for optimality, this is an optimal solution. Now, if we want to consider the case that B 1 goes up to 8 units, that means 3 more units are available here, and at node 5 you have 3 extra demands, right. So, 6. So, again the increase in the supply is also equal to the increase in the demand, right. Now, we want to consider how I can accommodate this flow in the current solution, so that I take advantage of the optimality criteria being satisfied, right. So, as we said, we will find out a unique path from 1 to 5, which is currently 1, 3 and 5, right, and find out its augmenting capacity, right. Now, in this case both the arcs are forward arcs. So, you can see that here the capacity is 3 units, because the capacity is for this arc is 6, and here the capacity is only 1. Therefore, the augmenting capacity of the path 1, 3, 5 is 1 unit, because I cannot see I may increase the flow by 3 units here, but then on the arc 3, 5 the flow will not be I will not be able to send 3 units from 3 to 5, only 1 more unit, right. And this is that is why you see. So, the augmenting capacity of the path is 1, and then 3, 5 becomes a blocking arc, right. So, anyway, I will then augment the flow here. So, that means this becomes 4 and this is also 4, and now you see that 3, 5 is a blocking arc. 1, 3 still has some positive capacity left. So, no problem, 3, 5 becomes a blocking arc, and as we said, we will then say that if I drop this from the tree, what is the cut I will get. And so, if you drop this, you see the nodes 1, 2, 3, 4 are on one side, and 1 belongs to that this subset, and then this is your other set S2, S1, S2. So, your cut S1, S2, as I was saying, this is a partition of the node set, and node 1 belongs to S1 and node 5 belongs to S2, right. And then the cut sets are the possible arcs, as I said, from either S1 to S2 or S2 to S1. So, you can in this network you can see, because this is your cut, this is your cut, and you can see that 3, 5 of course, we are going to drop, then the backward arc is 5 4 and the forward arc is 4 5. So, these are the 3 arcs that you have. This is not valid. 4 5 4 5 has no flow on it, there is a positive capacity. So, therefore, this is a valid arc because it is a forward arc. 5 4 is a backward arc, since there is no flow on 5 4, right. So, again this is not valid. So, this is what we meant by saying that 4 5 is a valid arc and it is the only one. So, therefore, I cannot really if we had more than one valid arc, I would have chosen the one with the minimum relative cost, but here I have no choice. 4 5 is the only valid arc, the capacity is 4 for this arc, and so now you look at the augmenting path, because you see 4 to 5. So, you have to have a path from 1 to 4 and then 4 to 5, right, and it turns out to be the path is 1 3 4 5. Okay. See, I am talking about the sensitivity analysis here, but later on also when we do max flow, hopefully you will have a better understanding as to how to go about finding an augmenting path or a path with positive capacity and so on. So, we will not spend unnecessary time on here or here. When we talk of max flow, the things will become clearer. Okay. So, anyway, the augmenting path is 1 3 4 5. It's a small network, I can show you immediately by looking at the network, but otherwise there are regular procedures to find out augmenting paths from one node to another. Okay. So, now the capacity of this augmenting path 1 3 4 5. So, 3 4 you all have a flow of 3 units, therefore, increase of 1 unit. Here of course, we saw that the flow can increase by 2 units. So, you have to take minimum of 2 comma 1 and then comma 4, because this has augmenting capacity of 4 units. So, the minimum is 1, and therefore, the augmenting capacity is 1 unit of this path, and I will increase the flow by 1 more unit. So, therefore, this will become +1 +1 and 4 5, which I have shown you here. So, now the augmented flow is 5 units here, this is 4 and this is 1, right. Okay. And now immediately you see that the arc 3 4 is a blocking arc, because I need still to find out if I can send 1 more unit of flow from 1 to 5. So, so far I have augmented the flow by 2 units. Okay. Now, when I drop the arc 3 4 from the tree, then you see 1 2 3 will be your first set of the cut, and 4 5 is the second cut of second part of the cut, right. And then the cut set you will have only 2 arcs, 2 4 and 3 4, right, because now your cut is this. So, 3 5 is already saturated, and 2 4 is the one which has positive capacity, because it is not being used, and 3 4 is already saturated, because I am dropping it from the tree, right. So, therefore, 2 4 again is the only valid arc. So, hopefully, in the assignment sheet I will be able to give you a problem in which you have more than one valid arc, and then you will have to make the choice by the relative cost of the arc. Okay. So, then 2 4 is the only valid arc, and augmenting capacity of this path is again 1 2 4. So, the path is 1 2 4 5. Yeah. So, this is the path 1 2 4 5, and the capacity here is 1. Here of course, it is 4, here it is 3 now, because you already have 1 unit of flow on it. So, therefore, the minimum would be 1, and so 1 2 becomes the flow becomes I should not do this, because this is regular. See, this is the thing is that I had a choice of making this a non-basic arc or a basic arc or more of them, but anyway our this has been that when you are dropping a arc, then it becomes non-basic. So, like 3 4 was a blocking arc. So, right now I am using the criteria that it is not in the basis. So, it is a blocking arc at its upper bound, it is a non-basic arc at its upper bound. So, we will maintain 1 2, even though it at its upper bound, I will maintain it as part of the basic tree. Okay. So, therefore, 1 more unit of flow you have here, and now you see that 8 units are being sent from 1, and 6 units are coming to node 5, 4 plus 2. So, the cost has gone up. I have not made a calculation of the cost, but the idea here is that you are maintaining optimality for the flow, right, and you can check. So, let us quickly check for optimality here. for example, what are the arcs that you need to for 2 3, or is it the arc is 3 2, right. So, here I have computed the dual cost. For example, for if you start with W 1 as 0, then this because the cost for arc 1 2 is 0. So, therefore, this will also be 0, W 2 will be 0, and then just make the calculation here for 2 4, what is the C bar 2 4 should be 0, because it is a basic arc. So, C bar 2 4 is 3. So, 3 minus 0 plus W 4 is 0, which implies that W 4 is minus 3, which I have written here. Then for 4 5, what is the cost? For 4 5, the cost is 1. So, 1 plus 3 minus W 5. Oh, okay. Why am I writing 3 minus 0 plus W 4? This is minus plus, okay, plus W 5 is 0. So, which implies that W 5 is minus 4. So, this is it, right. And now, let us quickly check for arc 2 3, 3 2, right. So, C 3 2 bar is 3 2 is how much? 1. So, 1 minus W 3, 1 minus W 3 becomes plus 2, and this will be 0. So, this is 3, which is greater than 0, fine, right. And what is the other arc? The arc you have is 4 3. So, C bar 4 3 will be equal to C bar 4 3, the cost is minus 1 plus W 4 I mean minus W 4 is so plus 3, and this will be plus W 3. W 3 is how much? W 3 is minus 2, which is 0. Okay. So, again optimality criteria is satisfied. For now you have 5 4, C bar 5 4, okay. C bar 5 4, 5 4 is 1. So, 1 minus W 5, which is plus 4, and then minus W 4, which is I mean plus W 4, which is minus 3, which is again positive. Okay. 5 minus 3 is 2, which is positive. So, optimality criteria is satisfied. For the you can check for these also, the optimality criteria would be satisfied, because the corresponding thing should be less than 0. So, the relative cost would be less than 0, right. Okay. So, this shows you that as I have been saying again and again, that the because of the simplified structure, the things become much simpler to handle. You can program them easily, and even the dual simplex pivot is easily handled, and you can do this kind of analysis, the sensitivity analysis, and you can find out the if the increase in the increase in the right hand side and the left hand side can be handled maintaining the same basic feasible solution, and if not, then you can very easily update the old solution to the one which can take care of the increased supply and demand. And so, the next thing that next part of the sensitivity analysis, see, the thing is that working with doing this sensitivity analysis gives you a better feeling for the algorithm. And so, now here the next part that we have to consider is changes in the capacities, which I hope to discuss in the next lecture. As to if the UIJs changes, then can you sort of find out what are the kinds of changes which will permit the current solution to remain optimal, because increased capacities would mean in some cases increased flow in the network, and then you would want to of course make sure that the increased flow is either it helps you to reduce the cost, that will be the first priority, and then of course, you can see how other things can be handled, how can it be handled if the capacities go up. Okay.